It's still going live. Okay, we are live now. Okay, so this is lecture 8 of Algebra and Computation, and so today's lecture is going to be the last lecture on group theory, part 1 of this course. And I've sort of broadly divided the lecture into 2 parts, where the first part is I just want to complete a few things about blocks and in general what is known as primitivity, which I'll define soon. And I mean, like we discussed a few sort of computational tasks involving blocks inside a group action. So that's what I'll do first. And after that, I'm going to sort of ramble a little bit about this general divide and conquer techniques. Okay. My goal is to give you an overview of some of the techniques that are done in in this part, this setup in general. I mean, like if you want to use computational group theory to solve certain problems, this is typically how you often make progress. You try to build sub problems that you can solve and and somehow combine these questions, combine the answers that you get in some meaningful way, etc. And that's what I want to do, and I want to illustrate it by giving you a high level picture of how you do degree 3 graph isomorphism. Okay, and but if you want to know the full proof of it and so on, I mean, like the notes from 2017, it has the full proof. But the goal for today's lecture is going to just give you an overview. It's going to give you a high level picture of how these divide and conquer techniques work. In fact, let me start by giving you a rough perspective of how you do something like this, and then the rest of them will sort of, hopefully the roadmap will be clear, at least where we are going as and when we define these objects and so on. So I want to sort of start off again with the Rubik's Cube. Okay. And this is something that you often do when you're trying to solve the Rubik's Cube on your own. That if you wanted to figure out a solution to the Rubik's Cube, you will often do something of the following situation, which is that you first think of it as saying that, oh, there are basically 54 stickers on it. So because there are 9 stickers in each face and there are 6 such faces. But then you tell yourself that, oh no, but not all stickers are the same in some sense. So some stickers are substantially different from other stickers in the sense that some are what you will consider as corner stickers. These are things that are there in these corners, right? And there are 8 corners and each corner has 3 stickers. So therefore that's 24 corner stickers. Okay. And similarly, there are going to be 12 edge stickers, which are these stickers, whatever, those sort of stickers. There are 24 edge stickers, which again is like there are 12 edges, but each edge has 2 stickers. So there are totally 24 edge stickers. And then there are 6 centers, which often you end up ignoring in the sense that you will put stickers using the centers as some sort of guide, because the centers tell you which color goes where or something. Okay. So in other words, what I've written here is really, if you look at the Rubik's Cube group acting on these 54 stickers, these are the orbits that you end up getting. Okay, so this is the orbit decomposition. Okay, and what's the point? Why are we mentally doing this orbit decomposition? Because often when you're thinking about solving a cube, you'll basically say something like, okay, I'm going to forget about edges. I'm going to first solve the corners. Let's just do that first. Maybe that's one thing that you do. Then you will say, okay, now I want to solve the edges, but in a way that I don't mess up whatever I have done already. Okay, so then you solve the edge stickers, and hopefully centers is something that you maintain in the process. But in general, you might then want to come up with a way in which you cycle centers or something of that sort. I mean, these could be one approach to do this. Okay, now let's ask ourselves, how did we mentally start thinking about solving 24 corner stickers? And there you will actually notice that, well, these 24 corner stickers are actually grouped into some form. In fact, they are grouped into 8 blocks, because each block literally consists of, it's like a block of a cube, like one of these corners or something, which has 3 stickers on it. So there are 8 such corner blocks. So if you forget about the actual orientation of whether or not the blocks are twisted, etc., you can say, look, the Rubik's Cube eventually acts on this bunch of 8 blocks. It moves these 8 blocks around. For example, if I turn the right face, somehow these 4 blocks are maybe turning clockwise. or something of that sort. So you could simplify your problem by just saying, okay, forget about the cubes being twisted, whatever the cube is being twisted, etc. Can I first get these blocks in the right place? So you somehow reduce your complexity from being something involving 24 stickers to something involving 8 objects or 8 blocks. So similarly, you can do the same thing for edges, and you notice that edges are made up of 12 blocks actually. Each block has 2 stickers on them. So therefore, a natural approach to try and solve a cube would often be you forget about everything and try to put the corner blocks in place. You don't worry too much about the orientation. Just somehow figure out a way of moving the corners into the right place. And now you come up with a way of moving the edges into the right place. And then you somehow come up with a way of untwisting them in some sense. Okay, so this is roughly the outline I want to give, in the sense that often when you're trying to solve some problems which involve permutation groups, etc., you try to make progress in one of these two regards. You look for orbits. Does your underlying space of all stickers, does it split up into distinct orbits? Yeah.
So one can ask, right? Means I don't know it's true or not. So the putting the corner blocks or the edges blocks in place automatically fix the other one.
Maybe, but let's say we are sort of, if you are, I mean, I can imagine situations where you can do things where you only move the corners around, but the edges don't move at all. I mean, right now I'm being very abstract about it. So it may be the case that, when I move the corners, edges also move in a very predictable way. But I'm just, as first principles, the most natural thing to do is like, let's fix one of them first. It might mess up the other thing a lot. But then once I fix the corners and now I'm fixing the edges, now I need to be careful about not unfixing the corners in some sense. Whatever I've already put in place, I don't want to mess that up. Okay. But this is, I mean, like, yeah. So the last time, etc., when we looked at a few examples of things that moved 3 edges around or something, they didn't do anything to the corners. So we could come up with some sequence of moves that did that. But on a high level picture, this is roughly what you did. Okay. You basically kept trying to break down the problem either in terms of orbits or in terms of blocks. Okay. And the hope is that once you do this sufficiently often, like it might be the case that, once you break down in terms of orbits and you do one level of blocks or something, I mean, maybe some other, the group becomes small enough that there are newer orbits, etc. It's just that it's a mental picture of constantly trying to make progress in this, with respect to this task. So this is what I want to sort of roughly say when it comes to divide and conquer. I'll be more precise later on, but keep this as your roadmap, because this is roughly what you would want to do when you're solving a Rubik's Cube often. You'll basically think of orbits and like the corners and edges separately, and you tend to think of corners as blocks. I mean, you'll think of them as, you don't think of them as 3 separate stickers that are independently moving around here and there. They're not independently moving around. They're moving together. So the mental picture should have that. Okay, so that's going to be the roadmap, but things will get technical. So I'm just giving you this roadmap so that, you have a way of grounding it to see what happens and so on. So here's a brief recap of everything that we need for this lecture. Okay, we defined this notion of set stabilizer, which is you have some subset delta. This delta happens to be a subset of your stickers. Okay, and a set stabilizer is basically what are all group elements that shuffle delta within itself. Like it doesn't move any element of delta outside of delta. Again, I keep emphasizing this. This does not mean that it is like fixing them pointwise. I don't mind it if things within delta are shifted, are sort of permuted among themselves. Okay, and this was a very, very important computational task, primarily because the graph isomorphism problem reduces to this. So if you could solve the set stabilizer question efficiently, then we saw that you basically solve the graph isomorphism problem. And again, when I mean solve it efficiently, this is a subgroup. And what I'm going to ask for is a generating set. Like, can you give me a small generating set for this subgroup? And if we could somehow solve this problem efficiently, we saw that we could solve the graph isomorphism problem. And there are special cases where we could solve this problem efficiently, which was precisely when this delta happens to be a block. Okay, and if this delta happens to be a block, which is the case that, basically there are no fragmentation that will happen with delta as it gets moved around in a group. So formally speaking, for every group element G, either delta on the action of G equals delta, or they are completely disjoint. Such a thing is called a block. And if you just look at all possible movements of this block, you get what is called a block system. Okay. And the point was that for blocks, somehow set stabilizer is efficient. Okay. So we are going to use this as a way of making progress when we are given an arbitrary set stabilizer question and we want to solve it. We're going to try and make progress by instead trying to go towards blocks and use blocks in that regard. Okay, so just a bunch of definitions. Okay, a group, whenever a group acts on something, we will say it is transitive if it means that there is only a single orbit. That is, any sticker can go to any other sticker by an action of a group. So the Rubiks Cube on itself was not transitive because there were distinct orbits. There was an orbit involving corners, there was an orbit involving edges, and there was an orbit involving centers. So that is not a transitive action. But on the other hand, we saw that the 2x2 Rubiks Cube, which has how many? 24 stickers, that happens to be a transitive action because any sticker can go to any other sticker. Okay. Once you have transitive, you can now talk about what is called a primitive action, which is to mean that there are no blocks. Basically, there are no non-trivial blocks. Okay. So a transitive action group of a group G on some set of stickers omega is said to be primitive if it so happens that there are only trivial blocks. And what are the trivial blocks? Well, a trivial block is certainly any singleton is a block, just by definition. Okay. And similarly, if you take the set of all elements, or if you take an entire orbit, that happens to be a block. So when I mean there are only trivial blocks, I mean there are no blocks whose sizes are like strictly greater than 1 and strictly less than size of omega. Okay. So so an action that is transitive means that there is a single orbit. An action that is primitive means that there is a single orbit and there are no blocks. Okay. And when I mean there are no blocks, I mean there are no non-trivial blocks. Okay. So last class, we spoke a lot about blocks in general. We sort of spoke about the block kernel and the fact that you can find the block system, etc. But one of the things that we didn't speak about is like, can I even figure out if there are blocks in this action? That is, I give you a group G and I give you a set of stickers that it acts on. And I ask you, is this action primitive? Okay. So one thing, of course, we can check if the action is transitive, which is that, you just compute the orbit of one element and see if it is equal to all of omega or not. Okay. So transitive, we know how to do. Now the next question is, can I find out if the action is primitive? So formally speaking, this is the task. Okay, let's just say that I have a group G given by a bunch of generators that acts on some set of stickers omega, and alpha, let's say, is one such sticker. And now I want to know, can you find the smallest non-trivial block containing alpha? And again, by non-trivial, I don't want you to return a singleton. Give me something that has at least 2 elements. And if the action is primitive, maybe the smallest non-trivial block is all of omega. I mean, maybe there is no such block. Okay. So this is the first task. In fact, this is the only main task that we are going to do today. And the rest of it is going to be a high level overview. So what are thoughts? How do you approach this problem? Does someone have any ideas?
So a block was anything that either everything moves together to something else.
Yeah, that's
or
right. So this is the
inside.
definition, which is that for all G, I want either delta par G to be equal to delta or delta par G to be completely disjoint from delta. So there should be no situation where this is delta and this is delta par G. That cannot happen. So either they are the same or they're completely disjoint. And I want to know, is there anything, any non-trivial block that alpha is in? So, okay, let me create a subproblem and let's solve that subproblem, which is, let's fix a beta. Okay, we'll run over all possible betas in order to solve this task. Okay, but the subproblem is I give you an alpha and a beta, and I ask you, can you give me the smallest block that contains both alpha and beta? Okay, so what are some thoughts you could have on this? I mean, how would you approach this problem? So for example, let's go back to our orbits question. If I wanted to find out the orbit of alpha or something, what would I do?
Basically, keep applying the rule.
Yeah, and
Like-
basically you're trying to ask, what more do I need to add to this set in order to make it an orbit? Like, what am I forced to add to this set? So we basically said that, okay, right now my tentative orbit is just the set containing alpha. But if I apply a group element and I discover a new element beta, I'm like, oh, okay, that beta also needs to be in this set. So our tentative orbit set kept growing, and we kept wondering, okay, is there anything else I need to add to this? Are there any new points I need to add to this in order to make it an orbit? And at some point we stabilized. Okay, so let's ask something very similar, which is, what should we add to this set alpha comma beta to make it a block? And I want to be very conservative here. I want to only add things that I'm sure any block containing alpha and beta must also contain this. So in some sense, I should have probably said, what am I forced to add? Or what am I forced to add to alpha and beta in order to make it a block?
They are orbital elements.
Good. So which orbit elements of alpha or orbit elements of beta? I mean, right now they're both in the same orbit. So
Both,
therefore,
the orbit element of alpha, then other orbit element other than beta.
okay. So let's again, let's look at the Rubiks Cube example. So the Rubiks Cube example had, okay, for example, let's look at just the corners. Okay, think of it as consisting of 24 stickers. Okay, and the orbit element of one of these stickers is actually all the 24 stickers, all the corner stickers in some sense, but not all of them are in the block. Right, so yeah, but you're very close. So let me try and give one. So suppose this was alpha and this was beta. Okay, now I apply some group element G to both of them, and I'm trying to figure out what, I mean, like, what happens. I don't know, maybe alpha goes to some sticker gamma and beta goes to some sticker delta. Okay, now can you give me a situation where you know for a fact, oh, in that case I need to add one of them? At the moment, this alpha comma, or
When they are equal.
so for example, so suppose this was equal to beta, for instance. It just so happened that I found a group element G such that when alpha was applied, I mean, when the group element got applied on alpha, I ended up going to beta. But when it was applied to beta, I ended up going to delta. Now, what can I say for sure at this point? So in some sense, let's say delta is the smallest block containing alpha and beta. Okay. So just to be precise, what does this mean? It means that if delta par G intersect delta is either equal to delta itself or it's the empty set. Okay. So suppose delta was, I don't know, some element like this. This is my delta. In the sense that there is alpha and beta, but there are a bunch of other elements. I don't know what they are. Okay. And application of G maybe takes it in, I don't know, this is what my delta par G is going to be. Okay.
Okay,
Now,
so if it's not, I mean, it's not empty.
so I know it's not the empty set
So
because beta seems to be common. So if it is not the empty set, there's only one option. This delta per G must be equal to delta. Okay, which basically means you are forced to now take small delta into your block. Any block that contains alpha and beta must necessarily contain small delta. Right? Because you are forced to admit that delta per G and delta as the same because they have a non-trivial intersection. And that basically tells you that whatever new element you discovered right now, that must have been in the block that you began with. Okay, it's very similar to the fact how we used to discover orbits. It's just that the situation right now is different. You're trying to find one of these weird intersections and somehow use the weird intersection to say, oh, this basically means that these other elements must also be in my set. Okay, so here is roughly what I'm going to do. I'll find all how do I put this? Find all pairs gamma comma delta, okay, such that there exists some group element such that alpha beta when applied to G equals gamma comma delta. And by this I basically mean alpha per G equals gamma and beta per G equals delta. Right now I just gave an arbitrary element G and I just said, okay, suppose we ended up in a situation of this sort, then I know what to do. But one thing we might want to do is we might want to find out what are all possible pairs I can obtain. Like if I run over all possible group elements, what are all possible pairs of elements I can obtain? So let's first ask, and is this a task we can solve? In order to solve this task, what do you need to do? So yeah, go ahead.
This is just like, I mean, where all can alpha go and where all can beta go? This is orbits.
No, but you're asking for this together as a pair, right? Because it's not like alpha and beta are being acted upon.
Oh, on the same
element. But yeah, but you're right. I mean, what does it feel like? It feels like a certain computation.
Yeah, like some sort of intersection or something.
Is it an intersection, or you're basically looking for where all can this pair alpha comma beta go to? Right? Think of this G as acting on these pairs.
Like on G cross G.
No, it acts on omega cross omega because these are elements from omega.
Yeah.
So G is so you're basically G is acting on omega cross omega, and what we are asking is where all can alpha comma beta go to?
Sure. Yeah.
So this is the same thing as the orbit of alpha comma beta under G's action. But now G is acting on pairs of stickers. That is, it moves both stickers together. So this was one of the questions in your problem set, which was to take a permutation that I've given you, which acts on vertices, and come up with a way of making it act on pairs. Like there is a natural action on pairs. So therefore, if you looked at that representation, then what we are asking for here is just, can you find the orbit of alpha comma beta under G's action? Yeah, and this we know how to do. This is something that we have done for a while. So therefore, that is something we know how to do. And now we can now give our algorithm. I just state the algorithm, and hopefully this should be evident to you that this ought to work, but we'll formally prove it in any case. So here is what we are going to do. Initially, my tentative block is just a pair alpha comma beta. I mean, I don't know better at this point. Okay. One of the things I'm going to do is I'm going to compute the orbit of G acting on these pairs so that I have all possible gamma delta things in question. Okay. So this is let's say we pre-compute that. And now let's set our tentative block to be alpha comma beta. And now we do the following stupid thing, which is what I want to do is the following. At this point, I may have learned that, okay, this is my current delta. Okay, what I'm looking for is I want to ask, is there a particular group element G such that when I apply it on delta, I end up with something like this. Because if that happens, I know all of this must also belong to delta. Basically, that's what I'm doing. Okay, so we are just using the previous, the simple thing. We basically said, if I find the beta comma delta in it, then I know I am forced to add delta to my block. And that's what I'm going to do. I'm basically going to say, look at all possible pairs among this, whatever. I mean, there probably a better way of stating this, but I was basically looking at, look at all possible pairs in the current set delta. Okay, initially there was only alpha comma beta, but maybe as the course of the algorithm, as the algorithm evolves, maybe your delta has become larger. Okay, so pick up some pair gamma comma delta, and let's assume that the gamma and delta are different stickers. Okay, and now pick up all possible pi comma sigma, which happens to be in the orbit of gamma comma delta. Okay, and now when am I sure I can add a new element? Okay, if it so happens that, which basically means that I took this pair, that I acted upon on some g, I ended up with a pair pi comma delta. If it so happens that pi happens to be in my delta, but sigma is not in my delta, then I know I must add sigma. Right? This is basically saying this is what my delta was. I picked up some two elements here, and I ended up with two elements that look like this. Like one of the elements was already in my set delta that I currently have as my tentative set. But somehow it's not that both these elements are there. Only one of them is there. Then I know for a fact I need to add the other one. I don't have a choice because I'm in a situation where the blocks are intersecting. And if they intersect, they have to be identical. So that basically says, okay, in situations of this sort, add whatever was the other element. Whatever was the element that was not already present in your delta, add that to your set delta. And you keep repeating this. Okay, in some sense, you're basically, you're adding things that you are forced to add. Okay, so I hope the algorithm in general is clear, and the intuition is also clear, I hope, which is you're basically using this obvious situation where you know you have to add delta, and you are just expanding on this same idea. You're basically saying that if I'm in a situation where I have a current delta, I pick up some 2 points alpha and beta in it, and its image was some beta and, or let's say it was gamma and delta, for instance, but so happens that gamma was here already, then I better put delta also here. So that's this is the algorithm. So are there any questions on this? We haven't yet shown that this is correct, but I hope the algorithm is at least clear.
So I mean, yeah, we haven't seen yet if this is, I mean, correct, but like, so here we are, I mean, in this case, we are all still working with just pairs of elements. Like,
Yeah,
I mean,
yeah.
does it?
So
Yeah,
basically, in order for the previous task of figuring out what is the smallest block, if at all you want to find a non-trivial block, it must contain at least two elements.
Right.
So for every choice of beta, you will figure out what is the smallest block that contains alpha and beta. If any of these answers were non-trivial, then you know you have found one such non-trivial block. Okay.
So also here, like once you've started with some alpha beta, and let's say we end up adding some gamma to this, then can't we instead, like, I don't know if that would make things any faster or something, like instead of finding the orbit on like for just these pairs, like then start working with the triples to see where they are going.
So the algorithm first computes the orbit of all pairs. It just computes this at one shot.
Oh, okay. Then
you do that
then
once because that is never changing. You do that first.
Okay.
And now you say, okay, my current best choice of what delta is alpha comma beta, and I'll keep improving my understanding of what I think the smallest block is.
Sure.
Okay, so this is the rough idea of what is happening. Okay, so now one thing we need to now convince ourselves is basically, okay, we are at the end of it. One thing that is clear is that everything that we added to delta was forced to be added to delta. We didn't have a choice there. I mean, if there is a smallest block, it better contain all the elements that we added. That is okay. What is unclear is why did whatever I output at the end, why is that guaranteed to be a block? Like, am I going to realize that I was forced to add a certain element in the course of this algorithm? Okay, so let's try to prove by contradiction, which is say that suppose not. Okay. So what does that mean? It means that there exists some group element G in G such that if I look at delta intersection delta per G, this happens to be non-trivial. It's not empty, but it is also not full. Because that's the, I mean, this is the, I'm just writing the definition of what that means for this delta to not be a block. I'm just negating the condition for this. Okay. So now, okay, so now let's ask ourselves, so when can that happen? Okay. So suppose the situation was that this was what my delta was. Okay. And so let's for the moment assume that, you know, this G was made up of a bunch of generators. I mean, it can be written using the generating set G1 through, I don't know, GR. Okay. I started off with, let's imagine doing this mental picture. I start off with this delta. I apply G1. I end up with some delta 1. I apply G2. I end up with some delta 2, etc., etc. I keep applying GR. I end up with some delta R. But you are now telling me this delta R is basically what is equal to delta per G, because I've applied all the elements. And you're telling me that this guy has a weird intersection with delta, in the sense that it's not empty, it's not full. That's what I will call a weird intersection, something that shouldn't be happening. Okay. Now let's, for the heck of it, let's do this slowly and ask, okay, was delta 1 completely disjoint from delta or equal to delta? And let's look at the first point where this violation happens. Okay, there'll be some I, delta I, which has a weird intersection with some delta J. Because I'm expected to have each of them to be disjoint or equal. That's what it's supposed to be. But there is a first time where something weird happens. Right? So what will the picture be? So let's say delta I is the first time we have a weird intersection. Okay, so what's the mental pic? What's this thing going to be? This is going to be what my delta is. Okay, I applied some group element, some G1. I ended up with some delta I in this case. But had I applied a different group element G2, I seem to be ending up with something that looks like this. Okay, and I want to claim no, this, then there is no way I would have outputted this delta. I would have outputted something else. Okay, so let's do the following. So let's just say that let's pick up an element here and let's pick up an element here. That is, I'm picking up something in the intersection and something outside the intersection. Okay, so when this delta was applied using G2 and I ended up with this, something went to this dot and something went to this dot. Okay, let's pick up those 2 points. So let's call this gamma and let's call this delta. Okay, and now what I want to do is I want to just ask myself, what can I say about gamma and delta where I apply, let's say, G2 followed by G1 inverse? What would I end up getting? So let's say that delta went to this thing and gamma went to this thing. Okay, without loss of generality. Now, so what happens to gamma under G2 G1 inverse? G2 is taking gamma to this intersection point. G1 inverse will take it back to delta somewhere. I don't know where. I mean, because that was also in delta I. Something went to this dot from inside delta, so it will come back to delta.
But the other element will go outside.
The other element, on the other hand, this one is going here, but it has to now move outside delta because everything was in delta only went here. So nothing went to this point. So the pre-image of this must have been outside delta, which means your algorithm would have run over this pair, obviously. And at that pair, it somehow didn't choose to add this other element, which is a contradiction. So this basically tells you that no, there is no way my algorithm would have outputted this delta. The algorithm certainly has an opportunity to make delta a little larger. So that's it. So it must have added the pre-image of delta, I mean the image of delta under this group. I mean this group element. It must have gone somewhere. So delta must have been this guy instead. So that is a proof to sort of say why whatever the algorithm outputs is indeed a block. So is this okay? I mean, so it's not very different from an orbit computation. It's just that we are keeping track of pairs and the group acting on both the elements simultaneously in some sense. Okay, so now with this algorithm in mind, we now have a way of figuring out, given a group action, is it primitive? And if it is not primitive, we have a way of finding out a small block. Okay, so that's what we know. So previously we were saying that we wanted to do divide and conquer when it comes to transitivity or primitivity. So basically, if there are multiple orbits, I want to break it up. So in order to be able to do that, I needed to be able to find the orbits, which we had seen earlier. So intuitively, we now tell ourselves, okay, I want to break it up involving orbits. And now we are saying, suppose next question I wanted to ask is like, are there non-trivial blocks? And if there are non-trivial blocks, I want to be able to find them. And we have just seen an algorithm as to how to find them efficiently. What is unclear is how to use that. I mean, even if we find these non-trivial blocks, what do we do? So that's what I'm going to do in the next whatever time I have left in this lecture, which is to look at these divide and conquer methods and try to give a high-level picture of what's going on. Okay, and everything will come down to solving the set stabilizer problem. We are going to be trying to solve the set stabilizer problem because we know if we can solve them, we solve graph isomorphism. So this is what we are going to try and solve, and we are hoping to make progress. I'm not saying I will solve it in every situation, but I'm hoping that I keep making enough progress, and hopefully at some point I notice that there is sufficient structure in my problem that I have some other side way of approaching things. So Shantanu, did you have a question? No.
No, sir.
Oh, okay. Okay. Sorry. Okay. So let's first do the intransitive setting, which is the setup is the following. We are given a group G via a generating set, and we are given a subset pi of omega. I am using pi because I will end up using delta for a block, and I don't want to use delta here because it might confuse us into thinking it is a block. So I just have some subset pi of omega, and the goal is to find the set stabilizer. And again, by finding the set stabilizer, all we are saying is I want a generating set of this. Now, suppose it was the case that we just got lucky, and it so happened that there wasn't even a single orbit. It actually had multiple orbits, like the Rubiks Cube. I mean, the Rubiks Cube, we are trying to solve some problem involving the Rubiks Cube, but we noticed that, oh no, there are corner stickers, there are edge stickers, and there are center stickers. Okay, so let's split our pi also in terms of which of those elements in pi belong to the corners, which of those elements belong to the edges, and which of those belong to the centers. Because I know for a fact an edge sticker will never go to a corner sticker in any case. So if you are going to ask me to come up with a permutation that sort of shuffles pi within itself, I know the corner part of pi must shuffle within itself, the edge part of pi must shuffle within itself, and the center part of pi must shuffle within itself, because I have no opportunity of moving across these orbits. Okay, so which is why let's say in general, let pi I be equal to the intersection of pi with the ith orbit, with omega I. Okay, then what can I write this element as? By the way, I'm going to now cheat and change notation a little bit because it's just easier to write down. I'm going to write this as put a pi here and a G here. I mean, please excuse me for this because it's okay, but yeah. Okay, so can someone tell me what is a way of writing set stab pi of G in terms of these?
Like when you take the set stabilizers for like each of the pi i's and then take like the closure of the.
Yeah, closure is something that we don't know what to do, but let's again think in terms of the Rubik's Cube. What would you have done in the Rubik's Cube setting? You would basically say something like, let's forget about everything else, let's solve pi 1. Okay, once we solve pi 1, let's then address pi 2, and then let's address pi 3, etc., etc. So I'm just going to write that differently. So I'm basically going to say, let's look at the set stabilizer of pi 1. Okay, once we get this group, let's now stabilize pi 2. I mean, I'm writing stab here, but I hope you understand what it means. And I keep doing this, and then I stabilize whatever pi r. Okay, so this is just like saying, you know, we are doing some successive stabilizations. You're basically saying that, you know, let's first solve this problem, then once we have solved this problem, we'll now solve pi 2. Okay, and then solve pi and so on. So pictorially, this is sort of what is happening. So this is my omega, and omega happens to be broken down into blocks, omega 1, omega 2, and omega r. And this pi also got split into each of these things. And you're basically saying, let's forget about everything else. Let's just come up with all group elements that map this pi within it. I mean, all these stickers within itself. I don't care if these stickers get moved up. Now you get a certain subgroup. Now within that subgroup, I'm now going to ask, okay, can I now fix these stickers? Now I get another subgroup, and then I keep doing this. So in some sense, I'm making progress because my omega is getting smaller and smaller and smaller. Okay, so this is one way of making progress. We still don't know how to solve this problem, by the way. I mean, all I'm saying is that I'm trying to make the problem simpler in the hope that eventually at some point we say, oh no, this problem is easy, we can do that. Okay, so that is what you would do if it so happens that you don't even have a single orbit, you have multiple orbits. Then you know what to do. You can split it up in each block, each orbit separately. Okay, and now comes the more interesting part, which is what happens when it so happens that there is a single orbit, but it is not primitive in the sense that there are non-trivial blocks. So let's say that delta is a block, whatever, non-trivial block. Okay, we are actually supposed to compute whatever the set stabilizer of this pi, which at the moment I don't know what to do. But one thing I do know how to compute is h equals whatever set stabilizer of delta, because this is something we know how to do efficiently. Okay, is this okay so far? I mean, like so far I'm not doing anything. It's not even related to pi in some sense. But let's try and understand a little bit about what this h looks like. Okay, so here is a claim. Okay, I claim that h is a proper subgroup of G. Okay, if delta is non-trivial. So can someone say why this is true? That is, I want to say there are some elements of the group G that, I mean, in some sense that don't stabilize delta.
Otherwise, it would. I mean, otherwise, then you get. I mean, this is not a primitive.
Otherwise, you get that it is a primitive thing.
Yeah.
I mean, in the sense, okay. So in the sense that if delta is a non-trivial block, in particular, this delta is not equal to all of omega.
Right.
Which means there is some element alpha outside of delta. And because G acts transitively, there is a way of moving stickers from delta to this point alpha, which was outside. I mean, any such thing will move delta outside. It doesn't stabilize delta. So therefore, in some sense, this is a situation where your group is becoming smaller somehow. I mean, like, this group is a slightly smaller subgroup compared to the G that you're starting off with. So previously, what we were doing is we were breaking up omega into smaller chunks. And this part of it is going to be to try to break the group into smaller chunks. Okay, so this claim just follows from the fact that this delta is not equal to all of omega. And because it is not equal to all of omega, there are some elements in the group that didn't stabilize delta. So H is certainly a subgroup of a strict subgroup of G. Okay, so now let's do the following. Let's write G as a bunch of cosets involving H. Union. Okay, and what was our set stab? What are we interested in? We are interested in set stab pi of G, which was the set of all G in G such that delta per G is equal to delta. Sorry, pi per G is equal to pi. Okay, and I'm just going to write this as a union of I going from 1 through R of set of all G in AIH such that pi per G is equal to pi. Because I know that G equals the union of these things. So I'm just splitting this big set into which of those G's came from this coset, which of those came from this coset, etc., etc., which of those came from this coset. Okay, and let's give this a name, and let's just say, let's abuse notation and say that this is I going from 1 through R of set stab of pi, but in the coset AIH. Okay, so in some sense, if I can solve these problems, then hopefully I can combine them together and solve this problem. And I'm hoping I'm making progress by going to these questions because H is a smaller subgroup than G is. And Lagrange's theorem tells us that H is actually a subgroup of size at most half than what you started off with. So you're making some progress. Okay. But here is a problem, which is earlier when I said solve this question, I want you to compute this. What did we mean by that precisely? This was a subgroup. So we said, give me a generating set. Obviously, you can't write down this subgroup because it could be too large. So here it was like, give a generating set. Now, what the hell is this? I mean, this need not be a subgroup at all, because for one thing, even identity need not be there. Identity may not even be in the coset. Right? So when someone says, solve this, what are we supposed to output? I mean, I hope the subtlety is clear, because in the previous situations, this made sense because this was a subgroup. So it made sense to ask for a generating set. Here, this at the moment just feels like some arbitrary set of group elements. I have no idea what structure is there for this set of elements. Okay, but I'm fairly sure that it's not a subgroup because there may be situations where I don't even have identity here. So what hope do I have of saying that it is a subgroup? Okay, and so maybe a related question is, what is whatever set stab of AIH? So any guesses for what sort of structure do you think it should have?
is it the, I mean, could it be the coset of a subgroup of set tab by?
Excellent. So it turns out that if it so happens that this set is non-empty, it's actually a coset of this subgroup. It's very similar to what happened in this isomorphism thing that we saw last time, which is that if I gave you two graphs X and Y, and I asked, let's collect the set of all isomorphisms from X to Y. I mean, it was not a subgroup. But on the other hand, it happened to be a coset of the automorphism group if it was non-empty. And something very similar happens here. It just, I mean, this fact is not hard to prove, but hopefully you sort of, I mean, like, I mean, with more familiarity, it becomes clear that, you ought to expect some structure of this. Fine, it's not a group for a stupid reason, like identity is not there or something, but it seems to have all the flavor of what a group is. And if you just think about it a little more, you will be able to prove this fact, that if it is non-empty, it has to be a coset of set stabilizer. Okay, good. Now you know this is not some arbitrary set of group elements. It has some structure. But the problem still remains. I was supposed to output something. So previously, if I asked you to output a subgroup, I would have been okay with you giving me a generating set. But now I am asking you to output a coset. How does one output a coset? Like, what is a suitable, succinct representation that we can give?
Like a coset representative and a generating set for the.
Right. So you basically, what I will now insist that you give me an element tau followed by a generating set T, where this is an element of the coset or a coset representative, like Varun said, and this is a generating set for this guy. Okay, in the sense that this is basically made up of all possible elements of the form tau times this thing. So I'm going to give this subgroup as a given by a generating set, and I will give you one representative for that coset. So that's going to be the output that I'm going to expect. When I mean, can you solve this problem? What I'm going to ask for is give me a coset representative and a generating set for the subgroup, not the coset. Okay, so that's what we are going to ask for. So are things okay so far? I mean, like, we are basically trying to break down the problem and in the process inventing problems so that we can somehow recurse in some meaningful way. Okay, so therefore we can now talk about the fact that set stabilizer with respect to the group G is equal to whatever the union of these set stabs. Okay, and if we can somehow solve each of these set stabs in this sense, I am hoping to put them together for G. And just a mild thing, as the algorithm evolves, we might be dealing with set stabilizers involving subsets. So maybe this equation in terms of subsets also makes sense. I mean, because if this is the problem you're trying to solve, you might want to break up the problem into sub-problems. These are the sub-problems. So that's what you would do. So great, at least.
Sorry, I just got lost. How did we get H again?
So H was going to be the stabilizer of a block you found.
Right.
This was some subgroup you managed to find. And I'm just trying to use this subgroup in some meaningful way. Okay, and yeah, and notice that the number of cosets is also equal to the number of block elements. So this is everything is small right now. So things so far seems to be okay. At least we have phrased the problem. We haven't done anything with respect to solving it. We are just phrasing the problem in a way where it seems like we are making progress. Okay, and finally, I need to now say, let's for the moment we assume that we compute all the things on the right hand side. That is, we have expressions of this form. How the hell do we combine them on the left hand side? Okay, so what I mean is the following, which is I tell you that set stabilizer of each of the right hand side elements looks like tau I times t, where this t is a generating set for whatever set stab pi of h. Okay, so you ran each of these recursive calls, and somebody gave you an output of this form. Now, how do we put them together? Because the output here is also supposed to be a single tau followed by a single set. That's what I'm supposed to output on the left hand side. And what should I output? So I need to figure out what is the right coset element to give and what's the right generating set I'm supposed to give. Okay, and this is the part that at least I find a little tricky. But maybe I'll just pause for a minute to see if people have some ideas on what they would want to put here. I mean, normally the point is the coset representative is often very easy because you can give any element which happens to be in that coset, and that's a good representative for you, right? So let's just say that, the element we end up giving is maybe just tau1. I know tau1 was the whatever representative with respect to the first thing. I just give that. The question is what happens here. So suppose I just say this is equal to the generating set T. Okay. Now together, this generates the point tau1 times whatever. But what is unclear is how do I get tau2 from this? Because at the moment, maybe tau2 is also another element in the set stabilizer, because that was the answer in the second I equal to 2 setting. So how do I get that now? Okay, so this is a little weird, and it just so happens that, and this needs a proof, which I'm now going to skip, which is you don't just give T, but you give the following. Along with T, you add these other, this coset change sort of things. So tau2 you can now get from this because it is tau1 times tau1 inverse tau2. So you get that, and you use that to get everything. And you now basically need to convince yourself that whatever this coset is actually equal to this. Like you get everything that you want. Okay, it requires some thought, but I'm skipping this. But there is some reasonable way in which you can combine the answers. Okay, so now let's zoom out, and I'm just going to give you the algorithm to sort of which is like a wishful algorithm to solve the set stabilizer question. Okay, so this is what is going to happen. So what are we given? This is the coset stabilizer. So we are given a particular coset representative sigma, a group given by a bunch of generators, and I'm given a subset pi. And my task is to compute the stabilizer of pi with respect to the coset sigma g. Again, when I mean you compute this, what I want is give me a representative and a generating set for the subgroups. That's what I mean by that. Okay, and we are going to do the first obvious thing, which is if G happens to not be transitive in the sense that it breaks up into a bunch of orbits, then we are going to basically say, okay, let's break up our pi also according to those orbits. And let's solve the set stabilizer question iteratively. Okay, so this part is like what we had done earlier. There's no real change except that instead of a group, you now have a subgroup. But morally, nothing has changed. Okay, now comes the next part, which is suppose G was not primitive. Then we found one non-trivial block. We just saw an algorithm to do that. We found one non-trivial block and took H to be the stabilizer of that block. And now split G according to these cosets A1H, A2H, blah, 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 till ARH. Okay. And now we basically said, okay, let's solve all of these set stabilizer questions. And for each of those sets, you get some tau I followed by a generating set. I mean, that's the output you would have gotten if you recursively ran this algorithm. And then we combine all the output in the way I described above. Okay, so this is what happens if G happens to be not primitive. And now finally, the situation where you are stuck is if you are working with an action which happens to be transitive and it also happens to be primitive. That is, there are no blocks. I mean, there are no blocks to speak of. And at this point, you just say you do something desperate. I mean, okay. And this is the point where it's very problem dependent. Depending on the problem you're solving, you will try to somehow find some other additional structure that you have in order to improve. You make progress in some sense. Okay. And so this is very problem dependent. Okay. Actually, I don't know. Is it DANT, DENT, whatever. Huh. Okay. So this is the high level picture of how the general divide and conquer methods work. Okay. And I'm going to give you one instantiation of this. Again, I'll not do the proofs of it, which is the degree 3 graph isomorphism, to sort of see how the hell does a version of this show up there. What is degree 3 got to do with anything? Okay. But maybe this is a good point to pause and ask if people have any specific questions with regard to the general outline of this. I mean, so far things have been very vague because we are just roughly hoping to make progress, either by shrinking omega into smaller chunks or shrinking the group into smaller chunks. And in the group setting, the smaller chunks happen to be the separate cosets of H. And we are just trying to combine the, once we solve each of those smaller chunks, we are trying to combine them. Okay. So now let's look at a specific instantiation of degree 3 graph isomorphism. Okay, the setup is the following. I give you two graphs X and Y. Both of them have degree at most 3. By that, what I mean is every vertex has at most 3 neighbors. Okay, that's the same setting in G, that's the same setting in X and same setting in Y. And I want to figure out are X and Y isomorphic or not. Okay, now what did we do last time? We basically said that I want to use group theory. So I want to move to the problem of automorphisms, because that feels like a group theoretic question and it's equivalent to isomorphism. So we'll basically say Z is our giant graph involving both these graphs together. I want to look at the automorphism group and figure out, does anything flip the two? Does it flip the copies of X and Y in some sense? So we're going to do something slightly different here. Okay, I'm going to pick up a particular edge in this graph. Let's call that edge as UV. Okay, if they are isomorphic, this edge must go to some edge in this graph Y. Okay, I don't know which edge it's going to go to, but I'm going to run over all of them. Okay, so I'm going to look at a specific this thing here, and let's just call this A and B. Okay, now I'm going to ask for, can you give me all isomorphisms, sorry, all automorphisms of this big graph Z that map this edge to this edge? Okay, it'll become clear why I'm doing this. Okay, soon. And sometimes what this is often done is you add a bridge in the middle between these two edges and say you are looking for all automorphisms that stabilize this bridge. That is another way of stating the same thing. Okay, but basically what you're looking for is, can you now give me all, so let's call this bridge edge as E, or T of this graph is the graph Z, which is equal to a set of all automorphisms such that the edge E stays on the edge E. I mean, I don't mind it if the two endpoints swap or not. I mean, I'm okay with this edge sort of swapping, but I want this edge to stay where it is. It's just some sub question, because at the moment it feels like, why are we interested in the sub question? Okay. And the reason we are interested in the sub question is because of this amazing fact, which is that once you fix this edge in the middle, okay, if you have a degree 3 graph, the size of this automorphism group happens to be a power of 2. Okay, and the fixing of the edge otherwise it could be the case that, you know, if this is an end cycle and this is another end cycle, this edge could have gone to any other edge, so you won't get a power of 2 here. But once you fix an edge, it turns out that you basically can, I mean, it turns out to be a power of 2. Okay, again, if you want a proof of this fact, it is there in the notes. The proof is not hard. Okay, but there's a reason why I'm not doing it, because I don't want to get digressed into those parts. Okay, one could say, okay, it's a power of 2. What's the big deal? The reason it's a big deal is because it so turns out that any P group, by that I mean the size of the group is a power of a prime. Any such group happens to be nilpotent. Okay, you don't need to know what nilpotent is, but the more important thing is the following. If you have a P group that acts primitively, then actually the group can't be too large. The size of the group is xt equal to P. Which in particular means if your automorphism group, if it somehow acts primitively, if you manage to keep breaking it down such that you are in some primitive situation, then the size of this automorphism group is just 2. There are 2 elements in it, that's it. Okay, so the whole point is that if you run this previous algorithm, if it was transitive, you do something. You try and break the problem down somehow. And if it was not primitive, you do something. When you reach this situation, you will be in a situation where we are working with a 2 group, which happens to be transitive and primitive. In which case, it turns out the group you are working with is of size 2. So the doing something desperate is doing brute force. You just run over all possible elements and figure out which of them stabilize the thing and which of them don't. So you can very trivially solve the problem in this situation. And if you put them all together, it turns out that you can now show that degree 3 graph isomorphism now has a polynomial time algorithm, because you will end up solving a set stabilizer problem for a nilpotent group rather than a general group. And because you're solving it on some groups which have this sort of additional structure in them, turns out this divide and conquer is something that you can instantiate efficiently. Okay, I'm clearly hand waving a lot, but I want to give you the high level picture rather than going too much into the details.
So this only works for degree 3?
Yeah, so then bounded degree GI in general, he looks in the same paper, Eugene looks in the same paper, showed that is also in polynomial time. And in general, if the degree was d, then the running time is something like n to the order d squared. But these facts are no longer true. You need to appropriately modify them. Okay, it turns out that if you have a degree d graph, then the automorphism group is not a whatever d minus 1 group. That's not true. But there is some structure that this group has. It has a very concrete structure which is very similar to nilpotent, but not quite that. It's a more complicated structure about composition factors being small or whatever. Doesn't matter. But the key point is you can still say such structured subgroups, if they are primitive, then their size must be small. That fact turns out to be true. And that's what works for the bounded degree setting in general. So both these settings, you basically follow the same protocol of this divide and conquer business. As far as the algorithm is concerned, the algorithm is oblivious about this. If you find an orbit, you split your problem. If you find a block, you split your problem. The hope is that when you reach this desperate situation, you have something else to work with. And in both these situations, it happens that when you reach the desperate situations, your group is so small that you can afford to brute force over them. Okay, and that basically is how Lux's proof works. The trivalent graph proof is completely there in the notes. There is a very high level sketch of the bounded degree graph part of it also. But in my opinion, this actually has all the key ideas that you would want. The other part just has a few more technical hammers that you need to use. But if you just take those for granted, then I mean, there's nothing substantially different from the perspective of the algorithm. It's the correctness proof that requires this extra hammers and so on. Okay, so so this is all I wanted to say. Let me just briefly go over what we did today. Okay, so the first thing that we saw was the fact that the two things that are very useful when it comes to divide and conquer algorithm is if your group happens to be acting in an intransitive way, in which case you have multiple orbits, you can break things apart. Or if it so happens that it is transitive, the next thing you can ask for is, okay, can I find like some imprimitivity in the group? Like, is there a block that is present inside? Okay, and if you can find the block, it turns out that also gives you a way of doing this divide and conquer operation. So that the intransitivity will help you break down omega into smaller chunks, whereas the imprimitivity will help you break down the group into smaller chunks. Okay, and the first thing that we saw was how do you find a block? Okay, and the idea of finding a block seemed to be very similar to the idea of computing orbits, but it's just that you need to compute orbits in the right action. You need to work with the whatever things acting on pairs, and you compute orbits there, and then and in some sense the algorithm in a way, at least to me, it feels very natural, and hopefully you've seen the orbit computation enough that it seems reasonable to you as well, in the sense that you constantly try to keep adding things that you are forced to add. And then you argue at the end that, okay, whenever I have done doing this thing, when I'm no longer forced to add any new elements, what I should have is the closure in that sense. And that's what our block was. Okay. And once we had a block, we then sort of formally spoke about these divide and conquer methods. And this was the general algorithm, which is, if you so happen that you're working with a group that is not even transitive, then you break up your underlying set of stickers into blocks and break up the set you are stabilizing into those whatever orbits, and then you do successive stabilization. That is part one. Now, if you got unlucky in the sense that your group you're working with is actually transitive, then the next thing you look for is, okay, do I have blocks of imprimitivity? Okay, and if there is a block, well, great. Then let's find a subgroup which is based on that block, and let's split our group G into the cosets involving this subgroup, and let's solve the stabilizer question for each of those cosets. And this is something that fortunately is doable, because if it was non-empty, it happens to be a coset itself. The set stabilizer, the coset set stabilizer happens to be a coset of the original set stabilizer. So therefore, it makes sense to solve this problem, because there is something now I can return. And there turns out to be a way to combine the answers that you get for each of the cosets. Okay. And then there was this case of, what do you do when neither of them happens? And this is the part where either you find a different way of finding a subgroup of your group and work based on that. If you're not able to do this, you somehow hope that at this point your group is so simple that you can afford to do something really trivial, like run over all possible group elements, figure out which of them stabilize and which of them don't. Okay, and it so happens that in the degree 3 setting or the bounded degree graph isomorphism setting, etc., you turn out to be in that situation, because any special the sort of groups you are interested in, if you know it acts primitively, turns out the size is small, and that together will complete this proof. And this was used as a stepping stone to actually come up with the graph isomorphism problem, like algorithm for general graphs, but which is better than the brute force n factorial time. So there was Babai and Lux came up with an algorithm for general GI that ran in time something like n power root n. Okay, and so this was by Babai, Lux, and actually Babai and Lux came up with an algorithm which looked like n power 2/3, but it was improved to n power half by Zemliachenko. Okay, and if you're interested in it, all this is there in the notes from the previous time. I mean, but the key ideas we have already seen, and maybe this is a good point to stop. So yeah, so since this is the last lecture, let me just summarize all that we have seen in part 1 of the course, which is that when you're working with problems like graph isomorphism, etc., it turns out the group theory is very, very relevant. Okay, and because groups have generating sets of much, much smaller size, you could talk about computational problems involving massive subgroups of SN and stuff like that. Okay, and surprisingly, many of these natural tasks turn out to be solvable in polynomial time. Like on the face of it, membership algorithm seems like a rather tough thing to ask when your group is so large, but we saw that membership, etc., is something that we can solve in polynomial times. And we use Schreier's lemma again and again and again whenever you are working with some sort of recognizable subgroups of small index. Okay, and in the last lecture, we basically saw orbits and blocks, etc., with some divide and conquer strategy. Yeah, so this concludes part 1. So part 2 onwards, part 2 will deal with computation on polynomials, and we'll begin from next class. Okay, so let me stop here and take questions, and we'll also discuss a little bit about whether you want to have an office hour in the next class, just to, in case some parts of part 1 was unclear, and we can begin computation on polynomials, say, next Tuesday. Up to you. Okay, so let me stop here. So are there any specific questions that people have? Okay. Okay, so if there are no further questions, then let's break for today. I will anyway maybe send a message on Academy in case people would prefer to have an office hour this Thursday, where we go, and since you also have a problem set deadline coming up, if you have some specific questions with regard to that, etc., we can address those, because we're going to be switching gears, like, and working with polynomials and so on, which is not, I mean, we're not going to be using too much about what we have done this time. So it's going to be a sort of phase change. So it might be a good point to pause and, in case people have questions. So anyway, let's figure this out on Academy and then decide what we are doing on Thursday. Sorry, Thursday, yeah. Okay, cool. So let's meet on Thursday then.